All right, guys, welcome back. So we're going to go ahead and get started. Um, I have about 6 reactions for you guys to do before your exam today. And I'm kind of going to walk you guys through how I'm going to put everything together that we've learned over the past like 2 weeks and see how we're going to go about figuring out whether or not it's going to be an SN2, SN1, E2, or E1 reaction. So the very first thing, let's go ahead and get started. The very first thing we're going to do is we're going to look at our substrate, right? We're going to look at our alkyl halide and determine whether or not it's primary, secondary, or tertiary, or methyl, right? In this first one, we see it to be a secondary alkyl halide. So this tells us that this reaction can either go in 2 ways. So secondary can either go through a SN2, like a bimolecular reaction, or it can go through a unimolecular reaction. So it doesn't really narrow down much for us, which is why we move on to the next criteria, which is going to be looking at our nucleophile, right? So in this first one, we see that we have ethanol as our nucleophile. So what do we know about ethanol being our nucleophile? What makes a good nucleophile? Our good nucleophiles are generally going to be charged species, right? So here we see that this alcohol is not a charged species, which gives us a good indication that this is not going to be a bimolecular reaction. We're going to have to form a carbocation in this scenario. And this being a secondary alkyl halide, that is very much the case. So it can form a secondary alkyl halide. So let's go ahead and see how that goes. We're going to go ahead and bump off that chlorine atom to form a secondary carbocation. Once we form our secondary carbocation, we're going to have our ethanol come in, and it's going to attack that secondary carbocation. We're going to form an intermediate with that alcohol attached with an extra group, giving it a positive charge. So our next step is going to be our deprotonation step. So now that we've gone ahead and attached our nucleophile, we have to go ahead and stabilize this, right? We have to get rid of this positive charge. So what we can do is we can either use our leaving group, which is fine to use on this exam, but I would rather use a solvent because in this case the solvent is going to be the solvent is also the nucleophile, right? So it's not going to be really caged by anything versus this leaving group is going to be caged by the solvent, right? Because it's a chloride ion being caged by a polar, what kind of solvent? Protic solvent, right? So we have those hydrogen bonds going in and caging that leaving group, which is the whole reason why this is an SN1 reaction to begin with, right? We're able to form a stable carbocation that stays as a carbocation. So I prefer to use a solvent. So I'm going to go ahead and use a solvent to go ahead and deprotonate that hydrogen off of my intermediate. And once that happens, those electrons go back to oxygen, it stabilizes its formal charge to become neutral, and then we get our final SN1 product. But remember, anytime we make an SN1 reaction, anytime we have an SN1 reaction, we know that these are the same conditions for E1, right? So we're going to also undergo an E1 mechanism. So this is going to be SN1. And now we start off from the same spot, right? We're going to form that carbocation. But now we have these beta hydrogens, right? So here's one beta hydrogen that we could start off from. And our ethanol is going to come in, and it's going to deprotonate that beta hydrogen to form an alkene. And in this case, this is going to be a secondary alkene, right? We have 2 groups attached to that alkene. However, this is not the only beta hydrogen we have, right? We have another beta hydrogen. So instead of attacking from this, I guess, top beta hydrogen, we're going to go ahead and attack from the bottom beta hydrogen. So here's that bottom beta hydrogen. And our ethanol is going to go ahead and attack that bottom beta hydrogen. Instead of making a secondary alkene, we're going to make a primary alkene. So now with this E1 reaction, we form 2 products, right? Both of these products happen at the same time, but which one is going to be our major product? And our major product is going to follow Zaitsev rule, right? Zaitsev rule. And that's going to be this one that is di-substituted versus the other one, which is going to be mono-substituted. So Zaitsev rule right here is what we're going to follow for this E1 mechanism. All right. So moving on to this next problem, right? So again, same substrate here, right? We still have that secondary alkyl halide. Um, so we can still go through that bimolecular or unimolecular process for our mechanism. So we have to look at our nucleophile. So here we have a strong nucleophile, right? A strong nucleophile. So from initial glance, this looks like it's going to be a SN2 reaction, right? But we got to slow down, right? We have to look at what our solvent is. So looking at our solvent, what kind of solvent do we have? Do we have a polar protic solvent, right? Since we have a polar protic solvent, we're not going to be able to do a very good SN2 reaction, right? Because our nucleophile is going to be very caged, right? So let's go ahead and see what that's going to look like. So we see we have these hydrogen bonding interactions between our nucleophile and our solvent. So this cages our nucleophile, making it not as good as it could be. So in this case, we're going to go through another SN1 reaction. So this goes through the exact same process as we did before, right? So we're forming the exact same carbocation, right? Which means we're going to go through the same SN1 reaction, the same SN2 reaction. In this case, since we don't have, since it's not an alcohol like before, we actually skipped kind of like that deprotonation step, right? We don't have to deprotonate, but still we form the same product because of how caged that nucleophile is. So we still undergo SN1 and SN2. For our next one, now this looks a lot more like an SN2 reaction, right? We have a strong nucleophile, and then what kind of solvent do we have? We have a polar aprotic solvent. So now we're going to go ahead and do our backside attack. And actually, let's go ahead and give some stereochemistry here. So I'm going to put this on a wedge. So we have chlorine on a wedge. Then we're going to do a backside attack. And now we're going to flip our stereochemistry, because remember in SN2 we do an inversion of stereochemistry. And I'm just going to remember, since remember up there that was a SN1 reaction, right? So we formed the carbocation, which means we can attack from either side. I forgot to do that earlier, but that means this can, yeah. So I forgot to do that earlier, but that means we get both the R and S configuration for our product. So we're going to get the opposite configuration. All right, for our next one, we have a ring system here, and then we have, let's see, a good leaving group on here, right? So remember what kind of alkyl halide is this, right? So we have 1, 2, 3 carbon groups on here, right? Which means this is a tertiary carbocation. If we were to form a carbocation in this case, we would form a tertiary carbocation. And remember, what does tosylate look like, right? So let's look at what tosylate looks like. So this is what tosylate looks like. This is a very good leaving group because we have lots of resonance. So when this leaves and it has a negative charge on that oxygen, that negative charge can be easily distributed throughout the tosylate group because of how much resonance it has. Right? So whenever you see OTS, that's a very good leaving group. So in this case, look at our nucleophile. We have ethanol again, right? And we said ethanol is our weak nucleophile. And because of that, we're going to undergo an SN1 reaction, right? So let's go ahead and form our carbocation. So we form a tertiary carbocation. This is a very stable kind of carbocation. So our ethanol is going to come in, it's going to attack. Again, it's going to be a racemic mixture, right? We're going to attack from either the top and bottom. So we're going to form both enantiomers. And again, like we did before, we're going to have to do a deprotonation step because that oxygen has a positive charge from having an extra hydrogen. We're going to get another equivalent of our solvent slash nucleophile to come in and deprotonate, and we form our final product, our final SN1 product. And there's our final product. SN1. Oh, and this is going to be a racemic mixture, so we gotta make sure we show that. So again, remember SN1 means we can also do an E1 mechanism. So we're going to take our same carbocation, because that carbocation does not change. And now we have multiple beta hydrogens we can choose from, right? We have this beta hydrogen up top, and then we have the one coming off of that methyl group, right? So I'm not going to show the full mechanism because it's kind of self-explanatory, but depending on the beta hydrogen we remove, we can form these different products. And actually, looking at it again, we have another beta hydrogen. So we actually have 3 products in this case. So we have 3 products for this one reaction. So we have the SN1 reaction, and then we also have 3 E1 products as well. All right, so let's go ahead and move on to our next one. So we have potassium, or in this case, sodium butoxide, right, in a polar, what kind of solvent? Protic solvent, right? We have a polar protic solvent. So in this case, what kind of nucleophile is this, right? So we have a very sterically hindered nucleophile, right? So remember, with our E2 nucleophiles, our E2 bases, what we're going to be looking for is going to be a quote-unquote strong nucleophile that has a lot of steric hindrance here, right? So this is a charged molecule, right? We have a negative charge on that oxygen group, but then we have that terbutyl group attached to it directly. So it really is going to struggle to do those backside attacks because instead of the alkyl halide being hindered, well, in this case, it is still kind of hindered. It's now the nucleophile itself that's also hindered, right? So, and because of that, we're gonna go through a different reaction. So we have these beta hydrogens that we can take from, but which one of these is going to have an easier time of taking from, right? It's going to be the least sterically hindered beta hydrogen, right? So that's going to be this one right here on the methyl group, right? Because this one, it doesn't really have to do too much work to get to it. It's just going to grab whatever proton it can get and run with it. So in this case, it's going to grab that proton that's just out in the open like that. And again, we're going to bump off our leaving group to form our product. Finally, in this one, we have the same reactants as before. We have our strong nucleophile and our polar aprotic solvent. But remember, we have a tertiary alkyl halide, or not an alkyl halide in this case, but tertiary group. And because of that, there's too much steric hindrance, and that's an ugly 3. We have too much steric hindrance, so that this SN2 reaction will not occur. It will not occur via SN2. Instead, it will likely occur through SN1 or E1, but we kind of know how that goes. It won't go through SN2. All right, guys, so that's going to be it. So thank you, and good luck on your exam.